Okay, so in the world of medicine, our bodies have these incredible little defenders called antibodies. They're our frontline defense. But here's the thing. To design new drugs, we have to solve this one critical challenge. We have to find the exact spot on an antibody that grabs onto a threat, like a virus. It's a huge puzzle, and if we can solve it fast, it could totally change how we make medicines.
I want you to think about it like this. An antibody, it's like a microscopic key, and the virus it's trying to stop, that's the lock. Now, for the key to work, it has to fit the lock perfectly. The real problem is we usually only have the antibody's genetic blueprint. So the question becomes, how do you look at that flat blueprint and figure out the exact shape of the key's teeth, the part that actually does all the important work?
So, in biology, these teeth have a name, the paratope. It's just the specific little group of amino acids on the antibody that physically latches onto the target. And honestly, identifying this paratope is everything. If you get it right, you might just have a brand new drug. But if you get it wrong, well, that key is totally useless.
And that, right there, is the heart of what we can call the antibody locksmith problem. Being able to predict this paratope accurately, and just as important, quickly, has been this huge bottleneck in medicine for years. It's held things up, and researchers have been coming at it from two totally different directions.
So on one side, you've got what are called structure-based methods. These use a full, complicated 3D model of the antibody. And yeah, they're super precise, but they are also painfully slow, they're expensive, and a lot of the time, we just don't have that 3D structure to begin with. Then, on the other side, you have sequence-based methods. These just use the simple genetic blueprint. They are way faster, you can do them at a massive scale, but the trade-off has always been that they're just not as accurate. So you're stuck, right? It's this classic choice between precision and speed.
But what if you didn't have to choose? What if you could actually bridge that gap and get the best of both worlds? Well, this is where our story gets interesting. This is where a new tool, a kind of AI locksmith, comes into play.
And it's called ParaDeep. It's a deep learning framework, and it is designed to predict those all-important antibody teeth with really, really high accuracy. And it does it using nothing more than that simple amino acid sequence, the blueprint. It's built from the ground up to be both fast and smart.
So the big question is, how does it actually pull this off, right? How does it look at a flat one-dimensional blueprint and see a complex three-dimensional key? Well, ParaDeep's real power comes from this really clever combination of two different AI approaches, which creates this kind of, this two-part brain.
So ParaDeep's brain has two parts that work in tandem. First, you've got the context reader. This thing reads the entire genetic blueprint, forwards and backwards, to get the big picture, the overall meaning. And then, at the same time, you have the pattern spotter. It scans that very same blueprint but looks for tiny, specific details, little clues that scream, this is a binding site. By combining that wide panoramic view with a microscopic focus, it gets a much, much richer understanding of what it's looking at. The researchers behind this also made some just brilliant strategic moves. First, they realized that the two chains that make up an antibody, the heavy chain and the light chain, are actually different enough that they each need their own specialized prediction model. That was a huge insight. They also found that giving the AI a full-length view, letting it see the whole sequence at once instead of in tiny pieces, made it perform way better. And this is really clever. They taught the model to pay extra attention to the binding residues, because they're actually pretty rare. They only make up about 10% of the whole sequence.
Okay, but talk is cheap. The proof is in the performance. So the team put ParaDeep in a head-to-head showdown with the old standard, a tool called ParaPred, and they used a blind test set, data that neither of these models had ever seen before.
Let's start with the heavy chains. Now, don't worry too much about the metric names here, F1 score, MCC. Just think of them as scores out of 1 that measure how accurate the prediction is. Higher is way, way better. And wow, as you can see, it wasn't even a contest. ParaDeep's MCC score is up there at 0.685, while the old baseline, ParaPred, is all the way down at 0.410.
This chart just makes it crystal clear, doesn't it? I mean, look at that difference. This isn't just a small step up, it is a massive leap forward in our ability to predict these sites. ParaDeep is just playing in a completely different league.
So here's the bottom line. That huge leap in performance translates to a 27% relative improvement in predictive accuracy for these critical heavy chains. 27%. That is an absolute game changer.
And it's not a fluke. The story is exactly the same for the light chains. ParaDeep's specialized model again just blows the competition away, proving that its chain-specific strategy is a winning formula all around. This thing is the real deal.
Okay, so the tech is seriously impressive, we get that, but what does this actually mean for you and me, for the real world? What's the so what here? Well, this is where it gets really, really exciting. Look, having a tool like ParaDeep just puts the entire drug discovery process on fast forward. It means we can vet potential antibody ideas in minutes instead of waiting weeks. It means we can scan these enormous genetic databases for hidden gems without needing a single slow, expensive 3D model. And what that all leads to is scientists being able to more intelligently design the next wave of therapies for everything from cancer to whatever new virus is on the horizon.
You know, you don't even have to take my word for it. The researchers themselves put it perfectly. They said ParaDeep is well-suited for early-stage antibody discovery, particularly in the absence of structural data. It's a powerful, super-fast filter that points scientists to the most promising ideas right at the beginning of the process.
And that really just leaves us with this incredible question to think about. We've just seen how a smarter AI locksmith can find the teeth on a key just by looking at his blueprint. So now just imagine the future that unlocks. What kind of challenges could we overcome? What diseases could we finally conquer if designing that perfect antibody key became a matter of days instead of years?